So thank you very much to the organizers for inviting me. Thank you to everyone for coming. So I'm going to talk attacks on ring learning with errors problem, which is joint work with Yara Elias, Aiken Osman, and Kate Stang. This work was presented at Crypto 2 weeks ago. So to begin with, I'm just going to start with a little bit of a review of things that we heard this morning, just the general context. We're interested in lattice-based cryptography. Why? Lots of different reasons. So, for example, one reason that generates a lot of buzz these days is post-quantum cryptography. So the idea that for the public key crypto systems that we currently use today, RSA and East elliptic curve stuff, when a quantum computer becomes possible, it exists at scale, then we will have quantum polynomial algorithms for breaking these systems, so we're looking for kind of new problems and replacements. So lattice-based cryptography, a number of problems in lattice-based cryptography do not have known polynomial time quantum algorithms to solve them, so that's one motivation. So in terms of a little bit of history, we heard a whole wonderful talk this morning from Daniele on history and foundations of lattice-based cryptography. So I only have one pathetic bullet point here representing one piece of the history that he mentioned. So just to kind of give you a time reference frame, so 1997, yeah, we were just talking about 1997, almost 20 years ago. So, but another important piece of history is around the same time, the Hofstein-Pfeiffer-Silverman crypto system, which became as well known as NTRU, was also proposed, and that has now been standardized. So those two bullet points are just supposed to kind of give you a frame of reference in terms of time. We're talking about a field that's been active, over the last 20 years roughly. And then zooming forward to things that are of great interest to me and current applications. So in 2009, we had the breakthrough from Craig Gentry, who should be somewhere anywhere, but Craig Gentry's work on constructing homomorphic encryption using ideal lattices. And since then, a rash of work building on these homomorphic encryption schemes to solve important and interesting problems for real-world applications, so privacy applications such as electronic medical records, machine learning and outsourced computation, and things like genomic computation. So I could give a whole talk just on these privacy applications that are very, very, very interesting that come out of these constructions of homomorphic encryption schemes that come from lattice-based cryptography. So that's just kind of a very high-level introduction. Summarizing and partly intersecting with what Daniele said this morning. So again, this is just a snapshot, which is a selection of some of the problems that Daniele mentioned this morning, things that are very well known, things like the shortest vector problem and the approximate versions of that. So if you had SVP sub gamma, like the notation he was using this morning, the gapped shortest vector problem, as he said, not actually finding the shortest vector in a lattice, but being able to decide whether it's greater than or less than a certain value. A closest vector problem, bounded distance decoding is finding the closest vector, knowing the distance is bounded. And then finally, learning with errors, which he also mentioned this morning, proposed by Regev in 2005. So again, from comparing with Daniele's talk, you'll know that this is not a complete list of all of these problems. It's just a sampling of some of the ones that are related to this topic that I've been working on recently, which is the ring version of the learning with errors problem. So let's first talk about what is this learning with errors problem. So a very easy way to say it just from a high level without looking at any notation is, suppose you have a secret vector and then you give an adversary a bunch of samples. Can the adversary find the secret? And the samples will be a pair. The first entry is a random vector chosen uniformly at random, and the second entry is going to be an inner product with your secret, but plus some error. So that's this A is a random vector, and A inner product with the secret plus some error is the second component of the sample. And the learning with errors problem is if you're given a bunch of samples, the search version of the learning with errors would be, can you find the secret? And then the decision version would be just, can you even decide whether those samples were learning with errors samples, or were they just random vectors with two random entries here. So that's the learning with errors problem. And you'll see, we'll talk a little bit about parameters and hardness, because all of these things depend on the parameters that you select, of course. So you should see the n, s is in f q to the n up there. So n is the dimension of the vector space. Q is the modulus in the sense of how large are the entries. And then there's this important component here, which is the size of the error. So those are the three parameters that you want to be concerned with when you're interested in learning with errors, or ring learning with errors version of it. In order to estimate security, you need to estimate security in terms of those three parameters, Q, N, and the size of the error distribution. So typically we're going to talk about error distributions which are Gaussian, so we can think of the size as being kind of like the width of the Gaussian standard deviation. Okay, so then for various reasons, ideal lattice cryptography was introduced. So ideal lattices are generated by an ideal in a number ring, and they have kind of extra symmetries compared to just an LWE lattice that allow you to kind of save space and speed computations. So for that reason, the ring learning with errors problem was introduced by Lubashevsky, Pikert, and Regev. And you'll see I'm following the mathematical tradition of writing out the names of the authors instead of putting LPR. So in the rest of this talk, if I mention LPR, I mean Lubashevsky, Pikert, and Regev. But we would all very much appreciate it if computer scientists would also tell us the names of the papers they're referring to, because that would allow us to look them up. So the reason Brakersky and Vaikutunathan is listed on this search ring learning with errors as well is that the Brakersky-Vaikutunathan paper that used RLWE to give a construction of homomorphic encryption is the main thing that I personally work on in applications, is the BV schemes and the generalizations of the BV schemes in homomorphic encryption. And I'll mention another reason why BV is up there a little bit later. Okay, so what is ring learning with errors? So basically just think of it like, again, if you don't want to read all the notation on this slide, just think of it as instead of taking vectors, like the elements in a lattice for LWE, you just think of them as having n entries in a vector. Now just take those entries and think of those as the coefficients of a polynomial. So it's just shifting from thinking vectors to thinking polynomials. So every vector is now a polynomial, because you just take the entries of the vector and make it into the coefficients of the polynomial. So that's the kind of mental shift that you should be making. But then you say, oh, well, that's interesting, because polynomials, we're used to working with polynomials, and that makes a ring structure, which is very nice. Whereas over here in the vector land, it's not as clear how should you have a ring structure in the LWE setting. Okay, so let's be more precise. What ring are we talking about? What polynomial ring? So if R is written as a polynomial ring Z adjoint X modulo F, where F is monic irreducible over Z, and RQ is just the same polynomial ring modulo Q for Q sum prime. Let me point out that in some settings that some people do not necessarily assume Q is prime, but we're going to assume Q is prime in this talk. And chi is some error distribution on RQ. So a key point is, let me finish my sentence and then a key point is, what does this mean, this error distribution? So is that your question? Go ahead, what's your question? What? Yes, but we're going, so there's an important point. So we're going to have Okay, so I did say monic irreducible, right? So I'm talking about this is going to be a number ring modulo some prime, right? So whatever you want to, depends on how you want to think about it. Depends on like how does Q split? Is it like if a very common assumption, like an overwhelmingly common assumption is that Q splits completely, in which case you'll be looking at lots of copies of a finite field. If you had that it was inert, which I think we might hear about from Jeff later, then you would have a finite field but of higher degree, not a prime field. Okay, so let's get back to this point. Or actually, I'm going to come back to this point in a minute, this issue of the error distribution. But you should imagine from what I said about LWE that the RLWE problem is now very similar. That is, you have some secret, but now your secret is going to be a polynomial. So it still has n coefficients. You can still kind of think of it as a vector. You have your secret S, and then you have a series of samples. A is chosen uniformly at random from this ring, and E is chosen according to some error distribution, which we've kind of shoved under the rug for now. And the question is, if you had been given this a collection of samples, throughout this talk, I'll often use the script L to mean the number of samples. So the hardness of these problems is usually stated with these parameters n, q, and the size of the error, and like the number of samples that you're given. You could imagine for some problems that your problem might be easy if you had lots of samples, might not be that easy if you didn't have that many samples. Oops. So I better talk less and move my slides forward more. Okay. RLWE problem is given a bunch of samples like this. Can you find the secret? Or the decision version would be, can you even distinguish, are these RLWE samples or are these just two random polynomials? Let's go back to this point here. So this is kind of the key point of this talk, and a lot of people in the community are aware of this fact as well. But it really matters what you mean by choosing an error distribution on this ring. So what I'm going to maybe talk about just a teeny bit about the crypto applications, the homomorphic encryption that I told you I was so excited about. And in those applications, what happens is that to use the hardness of this problem as the basis for the crypto system, you encrypt things by selecting error vectors from this distribution, and you're working in this polynomial ring, mod q. And so what do? Let's place ourselves in the situation where q splits completely. This is a very, very common assumption for all of these applications. So what do? You look at, again, so think of this. This is like n copies of a finite field fq. And you think of fq, instead of being a mathematician, let's make this into like the real numbers here. Instead of being equivalence classes represented by elements from 0 up to q minus 1, we're going to shift it over. We're going to think of it as equivalence classes represented from q over 2 down to minus q over 2. And what does it mean to pick an error? A small error means pick it close to 0. Okay, so I realize a lot of this stuff doesn't really actually make sense. But what we're going to do is we're going to say we're doing things mod q. Instead of fq being 0 to q, we're going to move it over. It's basically q over 2 to minus q over 2. And small error means in the middle, that is close to 0. So when we do crypto applications, that's what we mean by this error distribution. That think of a Gaussian like in the reals, and now think of kind of discretizing this in a finite field. And what it means is that when we add error, we're adding small coefficients. We're adding a polynomial that has small coefficients in this sense. Okay, so is that clear? Okay, 2 questions. Go ahead.
Saying that n polynomial is small coefficients, also like some cases have isomorphism between the string all copies of that Q is a different sense.
Yes, and we will absolutely get into that, and that's part of the whole point, is that there's lots of things that you could mean. It all depends on what basis did you pick, what isomorphism did you pick to all of these copies of FQ. But I'm saying that for the purposes of crypto, what people will do is they will fix an F and they will fix a basis. So typically, this will be, just to be honest with you, getting down to the spoiler here. In reality, in applications, this is only going to be the cyclotomics and probably just the 2-power cyclotomics. So you're talking about a monogenic ring here, and you have a power basis, and that's kind of the canonical one. I'll show you an example later in the talk where if you pick a different one, it's totally broken, and you better not do that. But if you pick the canonical one, what it means is, when I said small error, it just means pick your coefficients, E sub I, of your polynomial E in that range according to a discretized Gaussian. Yeah, so we did make a simplifying assumption here. So actually, in a previous version of this talk, I kept in both the dual version and the R version, and we kind of stated as two separate things. So kind of LPR with R and LPR with R dual, and then we talk about when there's an isomorphism between them and stuff. But for simplicity in this talk, I'm just going to talk that the whole problem occurs in R. If you wanted to swap out R by R dual, and in some settings that wouldn't make any difference whatsoever, in some other settings it would make a difference, then you could do this whole same talk with R dual instead of R. Okay, so let's move on here. The only thing that I'm not really including in this talk that is kind of missing, I felt like kind of hearing the talks this morning and thinking about what was covered and what wasn't, I probably should have spent a little bit more time on this. But really, for those of you that don't really care that much about RLWE, or like, why am I even talking about this? Like I said on my first slide, the real reason is because of applications to homomorphic encryption. Other people are interested in signatures and stuff, but homomorphic encryption is a really exciting application of this stuff. And so what I probably should have included was a description of the actual crypto system that you use and a description of kind of the hardness results. So the reason that LWE and RLWE became kind of interesting problems, this is kind of alluded to this morning, is because of security reductions that were proved by Oded and in the LPR papers that relate these problems, LWE and RLWE, to the other hard lattice problems that were mentioned this morning. So the context, the reason for thinking and talking about this whole issue of RLWE and how hard is it is two things. Number one, awesome applications of the hardness of RLWE. Number two, we're showing these crypto systems, homomorphic encryption. And number two is the hardness results that relate RLWE to other hard lattice problems. So that's the background, which I didn't say on a slide here. Okay, so far I've talked about two different versions of these problems, search problem and decision problem. So obviously it seems like the search problem is harder, right? So if you can solve the search problem, you can definitely solve the decision problem. But in fact, there are cases where you can show that solving the decision problem is enough, that you can actually use the decision problem to solve the search problem. So this was shown for LWE by Regef, and for cyclotomic ring LWE by Lubashevsky, Bikert, and Regef. And in joint work with Kirsten Eisentrager and Sean Hallgren, we showed this in general for Galois rings, not just cyclotomic rings, under small assumption of 2. So here's where I want to make a kind of a distinction between what we call two different error distributions. So I'm just going to pause, and I'm going to give you my high-level point of view. And this may be somewhat controversial, and I think that a lot of people in this room don't necessarily agree with this. But I think it's an important point of view. So this error distribution that I talked about, I went into, I belabored this point, right? I said about how are we going to divide up representatives for FQ, and we're going to center it around 0, and we're going to pick things small. This is what we call the polynomial learning with errors problem, in the sense that this is how the error distribution was chosen. This is different from how the error distribution was chosen for when LPR does their proofs of hardness of these problems. And so in my point of view, like the one thing that I would want you to take away from this talk is that the error distribution, it matters very much, and there's two different ways to do it. And one is interesting for crypto, and the other is interesting for theory. And there are some rings for which they coincide. So that was my one-sentence version of my talk right there, is that there's cases where this is the distribution that you want, the error distribution that you want to look at. There's cases for the theory people of the error distribution that they want to look at. And there are rings for which those two are the same. Easy version of that is primarily the cyclotomic rings and some other rings. And that one is interesting for crypto and one is interesting for theory, and that they better be the same if you want them both to be interesting, which we do want them both to be interesting. So by crypto, sorry, I meant that was shorthand for homomorphic encryption, because I realized that for signatures there could be some other considerations that are interesting. Whether, like, people that are interested in whether RLWE is a hard problem or not. Security if it's related to crypto. So my point is that you won't have any crypto system if you take a random RLWE distribution and you move it over to PLWE and do crypto. It has to land in what we would consider a usable error distribution in the PLWE land in order for it to be interesting for crypto, because otherwise you can't do crypto because it's not small. Okay, so for those of you that are not on the inside loop here, here's a description of what's called the polynomial learning with errors problem. It was introduced by Brakersky and Vaikutunathan in their original construction of the homomorphic encryption scheme. And this is exactly what I said. So you think of some map from R, the ring, to a bunch of copies, essentially, of FQ. And you sample each coordinate as a one-dimensional discretized Gaussian. And this leads to a kind of an approximate n-dimensional discretized Gaussian. So this is sampling the error coefficient-wise in the polynomial ring, which is what I made a big deal about, is how we do it. Okay, so here's another way to do the error distribution. And this is the one that some people call the natural way. Some people call it the theory-approved way. There's different names different people give to it. And the point is that instead of taking your ring and thinking of it, here's your ring R, and the distribution I talked about was thinking of your ring as a polynomial ring with a specific choice of polynomial. If it's monogenic, you could think of this as being Z adjoin alpha with some power basis. The powers of alpha are the basis. If it's not, if you want to take the full ring of integers and you don't get the full ring of integers like this, you might have some other basis. But the point is you specified, this is what we call PLWE. You specified your basis and you chose your error coefficient-wise according to that basis. This is what we call the RLWE distribution. And what it does is it takes, it's almost the usual Minkowski embedding. So it just takes a ring and it puts it in n copies of C by looking at all of the complex embeddings of the generators of this ring. So here we have this map. Alpha goes to sigma. It's essentially like sigma 1 of alpha, sigma 2 of alpha, where sigma I are all the complex embeddings of this number field. There's a specific way that it's done in order to make things come out right, but the error distribution is now different. So now you have something which is sitting inside of complex space, Cn. And if you want to do, for example, a spherical Gaussian, you do component-wise in this complex space. Okay, So the point is that the image here and the image here are, of course, isomorphic. So there's some isomorphism here, and then you could think of this isomorphism as being given by a change of basis matrix. So a little bit going to Daniel's question from earlier, and this is in some ways somewhat related to some things I think that Jeff is going to say, is that there's nothing canonical about this choice of polynomial, right? You could take another representation for this ring too. So you could write this as z of x modulo f1 of x, which is something I'll do later. I'll show you an example of an insecure cyclotomic field if you take a bad choice for this f1. So there's all these different presentations of this ring. And they're all isomorphic, and you could think of them as being going from one to another as being a change of basis matrix. So the really simple and important point is that you have an error distribution here, you have an error distribution here, and this change of basis matrix converts one to the other. For crypto, you need this error to be small. By crypto, I mean for homomorphic encryption, for example. You won't be able to correctly decrypt if you start adding error that's really large. So here, for crypto applications, you need this error to be small. And for theory, when you talk about the hardness of this RLWE problem with this embedding, you need this error to also be small. You need it to be like, for example, a spherical Gaussian with the width of the Gaussian being given by sigma, one of the parameters of our scheme. Okay, so that's kind of my key point is that this is the theory, kind of theory approved error distribution. This is the error distribution that we care about for crypto. And there are some rings for which these two error distributions are the same. So for example, if you take the 2-power cyclotomic fields, you can show that you basically have an isometry here. You have this matrix is a scaled orthogonal matrix, and it essentially preserves distance. But as you can well imagine, in lots of other rings, this is not at all true. And so what is the notion of kind of preserving distance? So one of the things that we introduce in this paper is the notion of the importance of what we call the spectral norm. So the spectral norm of a matrix just takes like whatever if the spectral norm of the change of basis matrix, let's call it rho, means that if you took a unit ball in the originating space and then you applied this linear transformation to it, you would land inside of a unit ball in the target space. So the spectral norm is basically telling you how much did your error get distorted when you moved from one to the other. So that's very important. So what we did was, this is just what I just said. Distortion, the error, linear transformation, spectral norm is the radius of the smallest ball containing the image of the unit ball. So the point of this talk is to talk about attacks on RLWE and PLWE, actually. So I said that we had to set parameters n, q, and sigma. Sigma is the width of the Gaussian. And these are important problems to set n, q, and sigma properly so that these systems will be secure. So we should first think about not just the hardness reductions, but like what are the attacks that we know on these problems. So just kind of naively, clearly, and even like if you look at lattice sieving algorithms and things like that, you can clearly solve these problems of like finding a short basis, or I won't get into exactly how you do it in time 2 to the power O of n log n. There's also algorithms, which there were actually 2 papers on this at Crypto 2 weeks ago, BKW algorithms, which run in time roughly 2 to the O of n. But my personal favorite point of view is that you can also use polynomial time algorithms like LLL or improvements, for example, BKZ, which might not be polynomial time, but they're still pretty efficient. And you can find relatively short bases with these polynomial time algorithms as well. So in practice, what we do is we look at how well these attacks work, and we use these to set what we think the parameters should be, n, q, and sigma.
So what is PKZ mean?
Oh, I fell into my own trap. Thank you. Not Spencer Block. Not Spencer Block. Okay, so anyway, so I'm just going to give, just so you have an idea, like for those of you that live in RSA or elliptic curve land or something, you might be used to seeing numbers much bigger than this. 2 to the 31 looks pretty small for Q, right? We're used to Q is, 2,000 bits at least, or 4,000 or 16,000 bits or something. But for RSA, you're not looking at having 1,000 of them. So each polynomial in your crypto system, be it a ciphertext or a key or whatever, has this size in these. And that's one of the, I would say, the limiting factor of applications of homomorphic encryption is the size of the ciphertext, because whatever your dimension is, then you have n coefficients of this size. So basically n times 31 is the size of the ciphertext. And for example, like sigma is 8 would be a reasonable error distribution size. Okay, so what are the attacks that we know of? So to be honest, what you could tell from this slide before is that when setting parameters for using ring LWE, we're basically ignoring the ring part. All of this stuff has to do with LWE, and we're just saying, oh, well, we don't know any better attacks on ring LWE, so why don't we just set the parameters the way we would have set them for LWE? And that's what we have done in practice. So in this talk, I'm talking about kind of new or relatively new attacks that show you that you should be careful in general on ring if you're using ring LWE. So the attack on the decision version of what I call polynomial learning with errors is due to Eisentrager and Halgren and myself from SAC 2014. So the potential weakness comes when you have a number field defined by a polynomial f that has a root which is equal to 1 mod q. So if you think about it, like if we're starting with a number field defined by a polynomial f, we're saying, oh, that polynomial is irreducible over q. So it doesn't have a root equal to 1, for example. But what happens is when we introduce this modulus q, you could very well, especially since we often assume that q is split, we're basically saying, oh, well, actually, mod q, it has n roots. And what if one of them happens to be 1? So if you see what happens in that case, you can take your samples that are of this form, and you can evaluate them at 1. And if you look, you're given a polynomial a of x, you evaluate that at 1. You're given this other polynomial b of x, which you can evaluate at 1, b of 1. But you know a of 1, and if e was chosen, this is why it's key to remember that the coefficients of e were chosen to be small, mod q, that you evaluate this at 1. This is also very small, small in the sense of being close to 0, if you kind of forget that we're doing things mod q. So the only thing that you don't know here is s of 1. But there's only q possibilities for s of 1. So you can guess them, and you can check. If you guess s of 1 correctly, and you take b of 1 and you subtract off a of 1 times b of 1, then you would get e of 1. And if this were really an LWE or LWE sample, then this would be small. So you can check for smallness. So you take your first sample, and you go through the guesses, and you check for smallness, and you keep only the ones that are small. And then you go to your next sample, you keep only the guesses that already passed the first test, and you proceed accordingly until you've either kicked out all of your samples, in which case you say, oh, I don't think these were our LWE samples, or you're left with only one guess. If you're still left with more than one guess, then you should keep going. You should get more samples. So that's the algorithm. And what it does is it helps you decide whether this is an RLWE problem or LWE samples or not, but it also helps you find S of 1. So you get one piece of information about the secret this way as well. So now this is a very kind of naive, let's say kind of trivial attack. So actually what we're doing now in some follow-up work is looking at more subtle ways of distinguishing. And there are a lot of things that we can do that are better than this. This is just kind of very elementary. And I think a really good way to think of this is in a little bit more mathematical way. So if you look at number 1 up here, you might say, well, wait a minute, why do you care? Why did f of 1 have to be 0 mod q? Well, these things we're supposed to be taking, this is multiplication in a polynomial ring mod q. So strictly speaking, when you multiply two polynomials, you're multiplying equivalence classes. So you could be ending up with something which is this plus some multiple of f of x, right? Because it was z of x mod f of x. But if you evaluate at 1, f at 1 and get 0, then when you evaluate this thing at 1, that part will disappear. So that's one way of saying the same thing that's said very simply in number 1, which is that you get a ring homomorphism by evaluating at the roots. You can't just evaluate at any old thing, but if you evaluate at the roots, when you take this polynomial ring and you map down to fq, then you get a ring homomorphism. So what we've done here, this is like a simple version of the attack in two senses. One is we're using a very trivial way of distinguishing samples, right? We're saying something has to be small. All we need to know is that they're not uniform, right? Which is a much easier thing to be. It's much easier to just be not uniform than it is to be very, very small, right? So we're using a kind of a trivial test for smallness here. And then we're also using kind of a trivial map here. We're actually smashing everything down to one dimension. So we're already now working on extending these attacks in both of these directions. That is, using more sophisticated ways of detecting non-uniformity and using slightly more sophisticated maps. That is, mapping to, let's say, a two-dimensional space or other dimensional spaces. Question? That's right. So in general, we think of f as being, like I said, monic irreducible over q. But did you mean if it's divisible mod q, mod little q? Sorry, there's two q's, a big q and a little q. Sorry? Yeah, so the key point is for the attack to work, it's almost the opposite of what you just said. For the attack to work, you want 1 to be a root mod q, which will never happen for the cyclotomic polynomials. Oh, x minus 1, fine, yeah, that low. Degree 1. Okay, so what we did in our original paper was to show that with this kind of very simple version of the attack, you are led to consider number fields with the following 6 properties. And it's kind of interesting because I'm pretty sure that probably nobody ever wrote down these 6 properties of a number field and thought that they were interesting. So let me tell you what they are and why we think they're interesting, and then I can leave you with an open question related to this. So the number field k, so the first property that q splits completely, this was used in a couple of different places that I mentioned. It's not absolutely necessary, but it's, for example, the thing that it's used in a lot of applications, but it's also the thing that makes it so that you've got like n copies of fq when you look at rq. K is Galois over q. This is important for the search to decision reduction. As I mentioned, these are the 2 conditions necessary for the search to decision reduction for RLWE. Or I'm sorry, not necessary. They're sufficient anyway. They're definitely not necessary. So numbers 3 and 4, here this is, sorry, this is some kind of LaTeX garbling problem that I couldn't fix. But this one just says that the ring of integers, the field k is monogenic. That is, the ring of integers is generated by 1, this is supposed to be square brackets here, z adjoin beta. And number 4 is this transformation somehow that this, in our original paper, we didn't realize that it was the spectral norm that was governing it. It was just, we knew that if it was an orthogonal transformation where the scale factor was not too large, that we would be able to transform the error distribution from one into the other. And then the final 2 conditions have to do with being relevant to crypto. That is, number 5 lets you have this attack. And number 6 is, like for homomorphic encryption, Q has to be large. Like, for example, if you can take Q equals 2, then even like 2-power cyclotomic fields would be broken. But in general, for homomorphic encryption, Q is very, very large, like 128 bits or something like that. So, yep, we do use -1 next. Order 2 instead of order 1. So anyway, so those are those 6 conditions. And on a number field, so you just think, oh, that's kind of interesting. Can we find number fields with these conditions? And so we started looking at that a little bit. But the basic problem is that basically we have not found any number fields satisfying all 6 conditions. Any number field satisfying all 6 conditions gives you an example of an RLWE instance which is weak. So the main thing for the attack, f of 1 is 0 mod q. So for example, for 2-power cyclotomic fields, we can take a weak, I'll show you later, a weak choice for f1 so that property 5 is satisfied, but then it doesn't satisfy property 4 about the transformation to the RLWE distribution. The transformation to the RLWE distribution takes a nice small distribution and makes it into something wacky. So anyway, so we haven't found anything that specifically satisfied all 6 of these, but despite that, we have found instances of the RLWE problem that are weak, and we've done that by weakening some of these 6 conditions. So this is the work that was presented in Crypto 2 weeks ago with Elias, Osman, and Stang. And so we, as I've kind of indicated, we weaken these assumptions or these criteria in several different ways. So am I supposed to leave time for questions within the hour? Or? Okay. Okay, so I'll just keep going. Hopefully won't bore everyone too much. Okay, so certainly if you evaluate at 1, you'll get an attack. If you some other cases that are interesting are -1. If you evaluate at -1, but then there's even, oops, I thought I had a slide for this stuff. 1 and -1. Yeah, okay, it's a little bit out of order, but if -1 is a root, that'll also work. And in general, if you have a root alpha which has small order mod q. So if you think about how do you use this, number 3 is, maybe I'll go back to how the attack works. Where's the attack? Okay, here. So let's put an alpha everywhere here. A of alpha, S of alpha, E of alpha. E has small coefficients, and alpha is, E is a polynomial, it gets evaluated at alpha. Well, this looks totally hopeless to distinguish this from uniform, right? Because you've got all of these powers of alpha all the way up to alpha to the n, mod q. So it just looks like, ugh, it just gets all over mod q. You're trying to distinguish from uniform, right? But the fact is, if alpha has small order mod q, that means it'll be like alpha, alpha squared, alpha cubed, alpha, alpha squared, alpha cubed, something like that. So you'll have only a small set of powers of alpha. They get plugged into this and multiplied by some very small coefficients, and that gives you a small set of error values. So the error itself is not small mod q, but the set is small compared to q. So that's a different way of distinguishing. Again, it's not as subtle as just trying to distinguish from uniform. It's specifically enumerating a small set of possible error values and then checking whether you're in that error set. So that was one of the ways in which we generalized the attack, and that's what I mean by when I say small order, a small set of errors. So the size of this set would be roughly this, 4 sigma n over r to the rth power, where r is the order. So clearly you want r to be very small if you can. So this essentially just says that algorithm again, but with the modification that I just explained. And this says like what the running time, you can see the running time of this attack is proportional to q and the number of samples, and it succeeds, it's correct with this probability, which you can make that probability very close to 1 if the size of your set S is less than Q and the number of samples L increases. So that's how that attack works. There's also, let's say you had 2 as a root, f of 2 equals 0. Well, that doesn't look very good either, right? Because 2 to the n could already very well be larger than Q, so you're wrapping around and you're adding up all of these powers of 2 in there, and that doesn't look like very easy to distinguish. But under these conditions, you can show that you can actually distinguish in those settings as well. So this motivates a question which I'll state at the end, which is, for example, finding the residues mod Q, which are the smallest possible residues of small order, for example, how large they have to be, which is kind of like an opposite of like Artin's question. Okay, so these were the generalizations of these attacks, and so now we changed those 6 properties of number fields into the following. We have these properties, so for the polynomial time attack to work, certainly any of these things would be enough for the algorithms that I've described to you already. For moving between the attack on PLWE and the attack on RLWE, it's enough for this spectral norm to be small, because that means that these error distributions will be very closely related to each other. So it's one instance of the problem here can be transferred to an instance of the problem here and attacked, and it will still constitute attack on the original one. And then if you actually want the search to decision reduction to go through, that is to change your attack from an attack on the decision problem into an attack on the search problem of RLWE, for example, it would be enough for the field to be Galois and Q split in there. Okay, so what we did in this paper, we did about, besides extending these attacks, we did a couple of things. We constructed families of number fields which are weak. So the RLWE decision RLWE problem is weak. We also showed other types of PLWE instances that are weak, including 2-power cyclotomic rings with a badly chosen basis. And we gave code for the attack and ran the attack and gave timings and things like that, and then stated a kind of bunch of open problems in number theory which come from this line of inquiry. So let me kind of quickly go through all of those things that I just said. So the construction of the number fields or number rings which are weak instances of RLWE. So it's enough, I mean, basically, I've already said this, but here's the theorem, is that it's enough to have a number ring that satisfies these properties where the spectral norm satisfies this. Just again, this is sufficient but not necessary, right? There's been a number of different questions. For example, spectral norm is governing like how big the ball is that it fits inside. But if your error here gets distorted, let's say it gets distorted like this, you might have a very, very large spectral norm, a pretty big ball, but you still had an error that was pretty weird that you might be able to detect some way. So this is sufficient but not necessary. But as you could see from my parameters, like actually those parameters that I gave you, those were real live parameters that are used for a key exchange, for example. Q was 2 to the 31, N was 2 to the 10. So you're looking at something that's somewhere around 2 to the 20. I mean, that's pretty big spectral norm. I mean, you could certainly find tons of examples of number fields with spectral norm that small or that big. Okay, so here's a construction of a family which satisfies all those properties. And the reason that we did it this way, so we wanted a family of number fields F so that F of 1 is 0 mod Q. So this is a pretty easy, trivial way to get that. But plus, this is a very easy family to analyze. So we could easily write down what the discriminant was, could use that to get the spectral norm needed. So we needed this, basically we needed the spectral norm, and we needed conditions so that the ring of integers would be monogenic. And so these things all together give you that all those properties that we needed are satisfied. And so these are all weak instances of ring LWE, any number field like this. And you look at this, and this is actually not so different from 2-power cyclotomics, right? 2-power cyclotomics are defined by x to the n plus 1. So this is just something, you know, a little bit different. I mean, not Galois. That one of the key points is that it's not Galois, which is kind of interesting. So instead of taking nth roots of 1, you're taking nth roots of something else, and somehow that screws everything up in terms of being Galois. So in general, the roots of the mth cyclotomic polynomial have order. They always have order m. So they're going to be immune to this attack, as stated, in the sense that definitely 1 and 1 and minus 1 are not roots. Those have order 1 and 2, and in general, they're not going to have small order. So, did you have a question?
Yeah, going back to the attack.
More further back?
You know, so what's the bottom line? So you can attack the decision version, but not the search version. Right?
Yes. So for this family, or just in general?
For this family.
Yeah. So for this family, this is an explicit family of number fields where the decision version of ring LWE is weak. Weak meaning we can solve it in this amount of time with this number of samples.
Can you remind me what a
Oh, sorry. This was the change of basis matrix that I never probably wrote down was M. So think of M as being the change of basis between here and here. So let's say we were only interested in crypto and we happened to choose this number ring with this polynomial. Then we would do, like I said, and we would have chosen our error distribution here, and we would attack this, this field, and PLWE is broken, so we break the crypto. But in addition, we also wanted to show that these are weak instances for this problem, the RLWE problem. So in addition, we kind of manufactured these examples that satisfied this condition of this spectral norm was small. So
is there a formula for the
yes. Yes. Sorry, I didn't write it down. It's like roughly, in terms of order of magnitude, it's roughly like NQ to the N. That's roughly the size of it. So, and another thing is, for example, that we just check whether this is bigger than 1, because that's sufficient for the thing to work, but it also even works. We made the attack work in practice when tau was even very small, even very close to 0. So there are boundaries after which the attack doesn't work anymore. But I mean, these bounds here are not these are not tight bounds on when it will work. It works much more generally than this even. But this is just stated so that we could state abstractly a family for which it works. Okay, so like I think what you're identifying here is that the key point that's missing is that we don't have a search to decision reduction here because these fields are not Galois. And that's why I was kind of commenting on the comparison with the 2-power cyclotomic fields, which certainly are Galois.
Use the hook to expand this to Galois.
Yes. So the Galois is simply because for Galois fields where Q is split, we proved that a generalization of the LPR theorem that was for cyclotomic rings that said that if you can solve the decision version, then you can also solve the search version. And the search version was the one that has the hardness reductions to other lattice problems. So if you just think of this chain of hard kind of lattice problems, decision version is linked to search version, which is linked to the other lattice problems. And so what we're attacking here is what's used in crypto, which is the decision version. But we also, in order to be interesting for people that care about theory, we would also like to link it to whether the ring, whether the search version of RLWE is hard. No, these are not Galois. So this. For ring LWE, nothing better than what's known for LWE. In a sense, yeah. Yeah, so my guess is that the search version will turn out to be easy, but in this case, we cannot take our current attack and turn it into an attack on search. We just have one piece of information so far. So it could be separated. Oh, good. Go ahead.
And that would imply looking for family flags, so we short spectrum family.
If you say so. I'm mostly interested in what breaks the crypto, but some people in the room are interested in what breaks RLWE. Okay, so going on to this is, I mentioned this before. For example, if instead of using, like for the 2-power cyclotomic fields, which are the best possible case for our RLWE implementations, if you, instead of taking the cyclotomic polynomial, which is the minimal polynomial of this, if you took the minimal polynomial of just something else in the field, but which is pretty close, just add 1. So now take the minimal polynomial of that. Let's call that, well, I didn't give it a name, but here these are cryptographic size parameters. These are, as you can see, these are the size parameters which are used in, for example, the key exchange proposals. So this gives you an example of a crypto system or an instance of PLWE, which is broken by our attack. And it's also Galois, which is kind of nice. But the fact is that if you transform this error distribution back over here, it'll be all over the place. It won't be a nice RLWE instance. So that's the property that's missing here. So this one is one where it had a root which was -1 mod q, but like I said, the spectral norm is unmanageably large. So this is just a silly arbitrary set of experiments. This doesn't really mean that much, but it was just trying to give us an indication of how the spectral norm grows if you just choose random polynomials f of x. So we just let a and b be relatively small and looked at these defining polynomials. It doesn't really mean that much other than that it kind of convinced us that certainly you could have a lot of examples of number fields where the spectral norm was pretty small. So here's some actual attack times. So if you take, this is the parameters that I mentioned that were interesting. N was 1024. Q is roughly 2 to the 31. These exact parameters were used for the for a key exchange construction based on RLWE. And so we break this problem in like 13.5 hours using like 40 samples. And like I said, the only difference between PLWE and RLWE is actually transforming this error. So like I said, in practice, you generate the error here for doing encryption and other things. But if you want to test the RLWE problem, what you actually have to do is you have to generate the error here, which is very costly from a computational point of view. So just to generate the problem that you want to attack is the hard thing here. So generating RLWE instances was sufficiently time-consuming that before the crypto deadline, we only generated instances that were of this size rather than this size. But as you can see, the attack times, 25 seconds, 44 seconds, with roughly 20 samples, are very, very efficient. So from this table, the message I would like you to take away is that there's no difference in the attack time between PLWE and RLWE, but there's a difference in the time to actually generate samples, which that in itself should be enough to convince you that we do not use RLWE for crypto. We use PLWE for crypto. Oh, I'm so glad you caught that error here. So these are not examples of monogenic rings, okay? So but they're still rings that we attack. So like I said, there's lots of possible ways that you can alter F1. Okay, so how do I generate an instance that I'm going to attack here, PLWE? So I pick a secret. So this is all artificial, right? I mean, you could give me the samples if you wanted to, but we generated our own samples and then attacked them and then checked that we found the right secret, right? That's how we ran this simulation. We could have, if you had been participating, you could have done it for us. No. But so for this, what do? It's very fast to generate samples, and that's why, like when we show our homomorphic encryption for genomic computation or whatever, it's very, very fast. Why? Because the error is generated coefficient-wise, and it's small. So we're just taking a discrete Gaussian coefficient-wise. Okay. So, but for this, that's not how you generate the error. You go over here and you use basically, GPV sampling method or something like that, and you generate the error here, and then you push it using this change of basis matrix over here, both of which are somewhat costly. So if you were doing this for crypto, that would just be substantially increasing your encryption time. It wouldn't do anything for your multiplication. No, this is the this is the runtime for the attack. So this is once you've been given the samples, how long does it take you to attack it? It doesn't include the time to generate the samples. That's a good point, though. Maybe you should have put an extra column for the time to generate samples, and you would see it would be reversed. Okay, so now I've kind of gone over time, which breaks my cardinal rule of talks. Okay, so but this is okay. So hopefully I won't still be talking at the picnic time. This is my last slide. Don't worry. So all of this is very interesting. I guess the point I was trying to make is there's at least 3 perspectives from which I would hope that this work is interesting. One is for theory people that are interested in how hard is RLWE, because it does give us some avenues certainly to attack decision version of RLWE, and now even in upcoming work to attack search version of RLWE. And a second point of view, which is my point of view, is that this is very interesting from the point of view of crypto applications. When I say crypto, I mean homomorphic encryption. There are also signature applications, which are important too. And for those, we really want to know which rings should we pick. And kind of the answer that this work gives us is that we should stick with cyclotomic rings. Cyclotomic rings are very safe. They're immune to these attacks. They're very safe in the following sense. This isn't a proof that they're safe. They're safe in the following sense. They're immune to these attacks, and the RLWE distribution is essentially the same as the PLWE distribution. So they're rings for which these 2 problems coincide. That way, everybody's happy. The theory people are happy, and the crypto people are happy. And then the third point of view is, if you're a number theorist, because of these interesting new constructions of homomorphic encryption, new applications, we have these new questions coming up about number fields that maybe somebody else has thought about for other reasons, but probably they haven't thought about all 6 of them at the same time. So for example, these are kind of number theoretic questions. When is a Gaussian on RQ distinguishable from uniform when you map it down to FQ? Or if you map it to something else besides FQ, maybe a 2-dimensional space, a 3-dimensional space. So that is an ongoing area of trying to generalize this work. So second question is, you could kind of see from all of these properties and these reductions that it's very interesting to have rings R, which are both monogenic and Galois and a few other properties. So for example, being of cryptographic size. Are there fields of cryptographic size that are both monogenic and Galois? Yes. cyclotomic fields, maximal real subfields of cyclotomic fields, but are there any others? We don't know any others. We have a theorem that says the only monogenic cyclic Galois fields are these. I'm sorry, I forgot the citation for that theorem. It's several decades old at least. But we don't have, but that was including the condition cyclic. So could there be other fields that are non-cyclic, but which are monogenic and Galois? Galois cyclic, so they're Galois, so their Galois group is cyclic. But so then like a third question, and this is the one that I said was kind of related to, like it's like a reverse of Artin's conjecture, or whatever it's called, is, so what is the distribution of elements of small order mod Q? Usually, like when you think of Artin, you think, oh, well, what's the smallest primitive root? What's the smallest element that will generate the whole thing mod Q? Here we're saying, let's say you want order 3. What's the smallest element of order 3? That kind of thing. Could be. What is the smallest residue modulo of prime which has exactly order R in general? So we have a lot of interesting questions. Others that I didn't mention, for example, the relationship between having small molar measure and being fields of interest here. So I've characterized that at least fields that have small spectral norm will be interesting from this point of view. And it looks like fields that have small molar measure are interesting examples of fields where you get small spectral norm. So things like that, kind of characterizing the number fields or the number rings that are interesting from this point of view. So those are the 3 perspectives from which I think it's interesting. So hopefully that covers the areas of interest of everyone in the room, I hope. So thank you very much.